Welcome, dear students, to this session number 18 in the subject of industrial metallurgy. Uh, we are presenting the contents that would be covered in this session. Okay. In the last session, we concluded by saying that when you have drawn or when you have with you the phase diagram of a particular metal or an alloy system, and if you are interested in a particular composition and at a given temperature, then after locating the temperature composition point, these are the three things that can be known from the equilibrium diagram, the phase diagram. So let us take these up now one by one. The first information that you can have from the phase diagram of a material system is that you can know about the type and the number of phases that are present in the alloy system, in the metal system, under some given conditions of composition and temperature. Now I am explaining these things with the help of some examples. Suppose it was said that your interest lies in a copper nickel alloy which has 48% copper and 52% nickel in it, and it is lying at temperature TW. So the temperature composition point is given by the temperature composition point W. And now you are to tell that what number and type of phases are seen. You look at the equilibrium diagram. This equilibrium diagram has got three distinct type of phase regions. One is this upper region, which contains liquid solution of copper and nickel. It's a single phase region. The other single phase region is this solid, which contains solid solution of copper and nickel. And there is an intermediate region which contains a mixture of two phases, liquid solution plus solid solution in a given alloy. Now, if you see your point W is lying in the single phase region, so your answer would be that there is only one phase in the material system under the given conditions, and that's the number. But what's the type of the phase? The phase is a solid solution of copper and nickel. Similarly, if it was asked that our interest lies in a copper nickel alloy with 34% nickel and 66% copper, and it's lying at temperature Tz, you see the temperature composition point is given by Z, and Z happens to be lying in this two phase region containing a mixture of liquid and solid solutions. So your answer should be that, sir, when we are having an alloy of 34% nickel remaining copper, and that alloy is present at temperature Tz, it contains two phases in it, and those two phases, one of the phases is a liquid solution of copper and nickel, and the other phase is the solid solution of copper and nickel. We move to the next piece of information that we can obtain, or in which your interest would lie, that whatsoever phases, number and type is existing, what is their chemical composition. Now again we are taking examples, and students, whenever mind it, whenever your alloy composition and temperature are such that your material system is containing only one phase in it, the chemical composition of that phase has to be the same as is the chemical composition of the alloy in which that phase is being contained. So if you say that my interest lies in an alloy of 52% nickel remaining copper, and it is lying at temperature TW, the temperature composition state of this material system is being given by temperature composition point W, and W happens to lie in the single phase region solid solution. So because there is only one phase present in your alloy under these conditions, the chemical composition of this phase would be the same as the chemical composition of the alloy in which it is existing. So you will say, sir, chemical composition of the solid phase is 52% nickel and remaining 48% copper. Had your system been lying, suppose our interest lies in an alloy with 34% nickel and remaining 66% copper in it, and now it is lying in a two phase region, then students, if you are lying in exactly a two phase region, then there is a concept called the tie line concept which would be used. And what's a tie line? See, this is the temperature composition point. Start extending, drawing lines across this point, isothermal line, so and keep on drawing it till it cuts a two-phase boundary. So here you cut this two-phase boundary, the solidus line, and here you cut this boundary. And one more thing, see, liquidus line contains, when your material system is on the liquidus line, the bulk is still liquid, but some solid phase has begun to form in the system. So it's a two-phase line. Similarly, when you cool down and reach the solidus line, bulk of the liquid has transferred and formed the solid phase, but there are last traces of liquid which would still be seen when you are on the solidus line. So solidus line is also a two-phase line. So what I'm saying is that if you happen to fall into a two-phase region, then the temperature composition point should extend lines isothermally in towards the left and towards the right, until what until what to an extent this line has to be extended till the line cuts a two-phase boundary. So it cuts liquidus line, which is a two-phase line at point A, and here it cuts at B. Draw perpendiculars from A and B, and this A and B would now give you the composition of the liquid and the solid phase. See, this point A is toward the liquid phase, so this would give you the chemical composition of the liquid phase in the system, and it's 28% nickel. And because this point B is lying towards the solid phase, so this perpendicular dropped over here, which is cutting at 40% nickel. So the chemical composition of the second phase, the solid solution, or simply the solid phase, is 40% nickel and 60% copper. So students, like, it is like this that you find out that what is the chemical composition of the existing phases. I again repeat for your reference, if your material system is at a temperature and has a composition that it falls into a single phase region, the chemical composition of the phase is the same as the chemical composition of the material system in which it is existing. If your material system happens to fall in a two-phase region, then the tie line concept can be used. So if somebody asks you when can a tie line concept be used, if there are three phases or four phases, you cannot use this tie line concept. Even if there is one phase existing in the system, there is no need of using this concept, and nor it can be used. Tie line concept can be used to determine the chemical composition of the phases, but only when there are exactly two phases in the materials system. So now we move to the third piece of information that we can obtain from a phase diagram, that is the amount of each phase. Again, we are trying to explain this with an example. Now again, as was the case taken in earlier two informations, here again, if you are taking an alloy of composition 52% nickel, 48% copper, and it is at temperature TW, this is the state of the system defined by temperature composition point W. It's in a single phase region. The single phase is solid solution. The chemical composition of this solid solution is the same as is the chemical composition of the alloy, that is 52% nickel. And interestingly, if there is only one phase, the entire weight of this alloy is because of this solid phase only. So if you had taken 100 grams of the alloy and there is only one solid solution in it, what's the weight of that solid solution? The weight of that solid solution is also 100 grams. Same would have been the case if you were lying in a completely liquid solution region. But now, second case, if your material system is say 35% nickel system, is at temperature Tz, it happens to fall at point Q, and Q is in a two-phase region. So your material system is containing two phases, liquid solution and solid solution. When your system is containing two phases, who would give the chemical composition of these two phases? The tie line. P point would give the chemical composition of the liquid phase, that is 28% nickel, and R point will give the chemical composition of the solid phase or the solid solution, that is 40% nickel. And here, to find out the relative weight of each of these two phases, means if you had taken 100 grams of the alloy, what weight of the alloy is because of liquid solution and what weight of the alloy is because of solid solution, you come to a concept which is called the inverse lever rule. What is inverse lever rule? You consider this tie line as a lever. So PQR I have taken as a lever, and I'll be talking in terms of nickel. You can talk either in terms of copper percentages or you can talk in terms of nickel, but it's always better to talk about in terms of elements whose weight percentage is increasing from left towards the right. So you had started with 100% copper, and here you have 80% copper, 60% copper. It's more wise to talk in terms of nickel, which is increasing from left towards the right. We have 0% nickel here, 20, 40, 60, 80. So if you talk about PQR in terms of their nickel composition, P is 28, then Q is 35, and R is 40. So what does the lever rule say? The lever rule says that assume your temperature composition point to be the fulcrum of this lever. This lever is of length PR. It is pivoted, or it has fulcrum at point Q, and PQ and QR are its two arms. And what's the formula of inverse lever rule? Inverse lever rule would be used to find out the relative weight of liquid, and it would be used to find out the relative weight of solid. How would be that? That would be the ratio of either of these arms over the length of the lever. And why is it called inverse lever rule? Because if you are interested in finding out the relative weight of liquid, leave the arm towards that liquid phase and take the inverse arm, take the opposite arm. So what would be the percentage weight of liquid? The percentage weight of liquid would be QR, that is arm, one of the arms, over the entire length, that is PR. So this would be QR, which I have designated as B, over complete length, which is L. So it would be B by L into 100. And what would be the percentage weight of solid? Again, if you have to find out the percentage weight of this other phase, you have to take one of the levers. Because it is inverse lever rule, you would not take the arm of the lever which is along this. So you will take the inverse lever, or the other arm, not lever, the other arm. The other arm is PQ. So what would be the formula? This arm over this entire length into 100. So what would be the percentage weight of the solid phase? It would be PQ over PR into 100. The same has been shown on the next slide. So you can see that what is the amount of liquid phase? The amount of liquid phase which is on this side is B by complete L into 100, which comes out to be 41.67%. Now the amount of the other phase is 100 minus this 41.67, or you can again apply the rule for it. Students, I've written it wrong over here. It should be A by L into 100. So that again comes out to be 58.33. So I think these concepts and this information that can be obtained from the phase diagram for any material system under any temperature conditions is clear to you. I enjoyed it discussing with you. I hope you also enjoyed it and you have understood it. Thank you so much for your patience, and thank you so much for your time.